Hello everyone. Good morning, good afternoon, and good evening. Welcome to the RTDS Technologies User Spotlight Series 2020. This is week number 11, and that makes it our final week in this webinar series. I'm Katie Sidwell. I'm a simulation specialist on the sales and marketing team at RTDS Technologies, and I'll be your host and moderator today. This is our first time doing a major online event, in particular a recurring online event, so I can't thank you, our audience, enough for joining us, for sticking with us. We've had such great attendance and really great interaction, and we've learned a lot from our presenters and hope you have too. If you remember one housekeeping note from today, it should be that we are hoping that you participate in our post-event survey. It will pop up once you exit today's webinar, so if you could just take a minute and give us some feedback, particularly for topics you'd like to see in the future, that would be really great. And if you don't complete that survey today, you'll get an option in your email inbox to complete it, and we'd really appreciate that. I will also direct your attention to the Q&A widget in the top left-hand corner. All throughout the presentations today, we encourage you to submit your questions using this tool, and then our presenters will be online and responding to your questions in real time, because that's what we do. And after the presentations have concluded, as per usual, we will do a live Q&A and discussion session to flesh out some of the answers to those questions. If you are catching this webinar on demand after it's already been released, please still feel free to submit questions via the Q&A widget, and our presenters will respond to those questions via email. And by the way, if you have general questions about the RTDS, feel free to reach out to me directly, katie@rtds.com, or to others on the team or our general contact email. We're always happy to take your questions. And before I forget, please feel free to jump into the chat widget, introduce yourself, let us know where you're joining us from today. It's great to see both familiar and new names and seeing what a global audience this event has had. We have two very different, diverse presentations from RTDS Simulator users today, beginning with SEL POWERMAX validation using the RTDS by Asad Mohammad from Schweitzer Engineering Laboratories, and then finishing off with experiences with using the RTDS simulator as a tool in University Undergraduate Teaching with Bruce Rigby from etalumiSe. Let's begin by introducing Asad Mohammad. Asad received his Bachelor of Engineering degree from Geetam COE, India, in 2011, and his Master of Engineering degree from University of Idaho, USA, in 2017. Asad previously worked designing extra high voltage indoor substations and transmission systems. Currently, Asad works as a project engineer with the Special Protection System Group of Schweitzer Engineering Laboratories Engineering Services Division. Asad has been with SEL for about 4 years, working as a power system engineer, studying various microgrid systems for power system stability and protection. Asad has worked on several projects for microgrids, ranging from oil and gas to mines, chemical plants, universities, etc., and is very familiar with HIL testing. Please welcome Asad Mohammad with his presentation, SEL POWERMAX Validation Using RTDS.
Good day to all of you. My name is Asad Mohammad, and I'm an engineer with the SEL Engineering Services. And my area of focus is power systems, and mostly in control system applications with one of our products, the POWERMAX solutions, where we design control systems for stable electrical microgrids, remedial action schemes, and generation control. There's a whole profile of activities that we do as a consultant branch of SEL, Schweitzer Engineering Labs. So today I'm going to talk about how we use RTDS in validation of our control systems, what we built as a POWERMAX solution. And in particular, I would like to talk about one of the projects we did last year and which was commissioned this year, and how RTDS has been a really helpful tool in trying to validate our own control system and provide solutions before even we could make it to the site and commission the system. So let's get started. So what I'm going to talk about is the system. I can't go in much detail about it, but I'll just give an overview. Some of the problem statement as to what solution we were providing there, how we set up the simulation model, and how we set up the hardware in loop for testing, and what we did as SEL solutions in addition to the control system itself. The system is an islanded and isolated system. Well, what you can imagine is something very similar to imagine the power system on a cruise ship. We have a bunch of diesel generators running at their some amount of their capacity, and there is no connection to the grid to support them. So they're on their own. If the generators go down, they black out the whole system. This was something similar. It was on land, but it was still really important how it was set up. They had strict EPA regulations because of its location in Alaska, and they are required to operate at a particular power factor to maintain, to keep the emissions down on these diesel generators, and they cannot have all 8 of their generators online beyond a certain period of time. It is expensive downtime because obviously production loss is not acceptable for any customer. One good thing is all the diesel generators were of almost the same rating, so it was very helpful for us in a way to produce the simulation model. The load of the system was industrial load, so for a mine we'll have mostly industrial load, as in the sense of big giant crushing machines, belts, conveyor belts, heating, and whatever goes on to mines. There was no renewable energy. So just because we mention about microgrids, it doesn't always have to be renewable energy. So the reason to emphasize this is that if the generators go down, they're the only source of energy in that mine, and it's not acceptable. Any downtime is not acceptable. The simulation model, what we used, had to be built to an accurate model of the generators' loads with some small amount of approximations, but we modeled the whole generator system and every load, every induction machine, synchronous machine, and some static loads. We use the IEEE model of the generator, which is provided in the RTDS itself. And how we set up the hardware in loop was we set up 2 of the machines to be controlled by hardware, while the rest of the 6 generators we had completely built inside the RTDS model. By what I mean by that is that the governor and exciter were actual hardware equipment for 2 of the generators, but the rest of the 6 of them, we built them inside RTDS. So what we do, Special Protection Systems Group, and this is a wing of SEL Engineering Services. We specialize in power system stability studies, where we, at least for this project, I'm just going to talk about voltage stability and frequency stability. But there are some times where we have done much beyond that. It's what this project is still a tip of the iceberg. So generation control, this is a slow response system where we control the output of the generators based on the demand or whatever the customer requirements are, like tie flow control or regulating the output of generators based on, let's say, EPA regulations or efficiencies, things like that. Anything can be set up that way. Load staging solutions, this is the prime important one for frequency stability, such that we save the system from blackouts, SCADA, and then island-based or grid-based operations. This stretches beyond decoupling, synchronization to the grid, and a lot more that goes into it, but I'll keep it simple. And we have remedial action schemes, which is more widespread and not confined to microgrid systems. So goals for the system was generation control. We had to tune the governor and exciter in the lab. So a lot of pre-tuning was done before we even reach site. We provide protection for the generators and feeders. We basically a complete revamp of the system because the mine had an old system that they had been running for 30 years. And then another interesting thing we did was to improve the efficiency of the generators. Some motors that have VFDs on them, we were able to draw reactive power from those VFDs and use them as cap banks to improve the overall efficiency of the system. And then we do provide load shedding system as contingency-based load system. It's just the fastest load shedding solution we do. And then under frequency as a backup, and then PLSP, or a progressive overload shedding system, or a rolling average algorithm, which is like a very slow response-based protection. Let's say like if some of your generators are running at the max capacity, but there's a small amount of load that is creeping up, and your frequency very slowly starts going down. Instead of having to wait all the way, we go ahead and trip a small amount of load to reduce the load off of these generators. Let's go to the overall setup, how we set up in lab. What you see in front of you is the solution, what we did for just one generator. I know I mentioned that we used 2 generators, hardware and loop, but what we have here, what I'm showing here is simplified just for the sake of one. Let me just use my pointer. So if you see what we have here is RTDS. I just put a small one, but we are using the and this IO cube, or IO cube, what we call them, had the GTFPI and GTAO, GTAI cards in them. Using those, we used an amplifier, Doble amplifier, to amplify current and voltage signals, because there's no secondary injection in the governor and AVR. And we used that to provide to not just them, but also our feeder protective relay and the generator protection relay. And we also have, and based on that, they produce information, HMI SCADA information. So what do you see? Using the IO cube, we were able to feed speed to the governor, and the governor would provide the actuator set point. Basically, that is your control for the frequency of the generator. When you come to the AVR, we get EF from the AVR, and we feed the field current back to the AVR, and based on that, we get control from the AVR. Now, what the governor and AVR did with the 751 is provide all these points and the feeder protector relay. So this, what you see in the box, is the generator panel, which would go out in field. This was an SEL 751, and this is a SEL 700G. So this was the generator protection relay. While the 751 had some protection functions and also provided interesting control of the generator. So that was really important to test all this logic. Using the 751, we were any operator, although you can do this remotely from a central HMI, SCADA HMI, but an operator could go in front of the generator panel 751 and load and unload the machine. As in, when you load a machine or turn it on for the first time, like it would actually synchronize the machine and in steps slowly load the machine starting from 0 megawatts to 1 per unit, or wherever they want to go. And offload, if the machine is running at 1 per unit output, based on a ramp rate, once you enable on unload of the machine, the 751 would regulate the output to the governors, and the exciter not much, but mostly the P of the generator had to be controlled. And it would offload the machine until it went close to its minimum operating point and then trip the breaker. So it was a safe shutdown for the generator, technically. So having this hardware and loops set up was really helpful for us, because we could test all this logic, fix any issues, and basically avoid any kind of downtime on site. Let's look a little bit deeper. So as you saw in the overall setup, when you had the governor, we used the Woodward 2301E. It's a little bit more detailed here. What you see here is the Ieee governor model generator. Using the CT and PT inputs through the IO cube, we amplified those signals, fed that into Woodward. I forgot to put in here, but there's also a speed signal that is fed into the Woodward. And what you get out from it was the actuator set point, goes to the actuator model, to the engine model, and that is fed as torque to the machine. So the 2301E model this model is provided in ETAP. We use this model to create similar control for all the rest of the 6 generators. If you remember earlier, I mentioned that we have 8 generators, 2 of them hardware. So now not only were we setting up hardware in loop, but we also had to match rest of the 6 generators to behave similar to the hardware itself, right? So that's why we used this model, and then we did extensive testing to match both the hardware and the software controllers. This is the exciter setup, something similar, the same generator Ieee model. We have the RTDS, voltage and current go out here, they're fed into the ABB Unitrol. We get the PWM output, which is basically EF for the field voltage, and then the field current is fed as feedback. And this is the ABB AC7B exciter, which we used at that time. Now they use AC11B, I believe, for Unitrol, but this is what was provided back then. And we use this similar one to set up our exciter model. This is the design of the POWERMAX system. So another thing, in addition to all that, what you've seen, but most importantly was our product was to test all this setup. This is an example. This is not really how we used it in this system, but it's something similar. What we do is we use RTDS to generate all field data, especially required for stability, for load shedding system, for generator control system, and then eventually even some amount of SCADA for the sake of populating the HMI. So we have what we call them as front-end processors. These are like how it is sometimes on field, we set up all these so many FEPs spread over an area. So that feed them at the primary source, and then they centralized FEPs. And then that data is fed into load shedding processors and generator control systems. These boxes can have any kind of algorithms, but that depends on each system one at a time. And you'd have the gateway to convert the protocols, and then finally we display it on the HMI. This is something we did in our system too. So like I mentioned before, we use the 751 and 700G to load and unload generators. We provide power set points, generator mode control for ISOC group, volts, power factor. Generators would break based on after loading and unloading, or you could also do it directly that you would trip the breaker or synchronize it back into the system. Push button interface for generator control and remote control to centralized POWERMAX solution. So one you could do at local level and something at a higher level also. So this is what we did with rest of the generators, what I mentioned. So what you see in the drawing is that G2, what you see here, is actually the hardware, and G8 was the software model for all of them. What we did was to match the response of the hardware against the software. You might see some difference in the frequency when it comes to G2 and G8, but given the margin of error, we were satisfied with this result, because there was some amount of disturbance here, but which was unnecessary sacrifice that we had to do, given the time we didn't. So that margin of error or the percentage of error was acceptable to us. But if you look at the voltage that the exciter had provided, it was really close. If you can see how it tracks, and you can see the output of the generators hardware versus software. And this was the preliminary setup required to go to the next stage. Not only did we do that, we used these simulation PID loops for PID values, what we tested in lab, and we put them exactly as it is on site, and the response was totally acceptable, and the end user was happy that with the response of the system. And when some amount of transient tests were done, not studies, some amount of transient tests were done on site, the control of the governor and exciter was very acceptable, and we didn't have to change any values, at least as of now, which was a great benefit for us, being able to do all this at lab before we could go on site. Some interesting event that we also came across while doing all these tests. This is just an example, there's a lot more, but let's say we have in this system where we had 3 buses and a current limiting reactor. If there was a bolted fault or a 3-phase fault on bus 3, the voltage drop was so intense at that point that it would, even though we opened the breaker within 100 milliseconds, 150 milliseconds, if I'm not wrong, the voltage depression on the rest of the system was so great that it would trip these generators and throw the exciters out of whack. To avoid that, well, it was such a corner case, but the whole goal of this system is to provide a solution that we don't black out the system, right? So what we discovered was that using the system was that there was some very big machines on feeder F21, which were helping bring down the voltage even further down. They were huge induction machines. And when a voltage is depressed, it would draw a lot more current, and then it would bring down the voltage of the bus even further down. So what we discovered was one good thing to do was to trip this. And you can see in this plot that when we did the case, a bolted fault case, you can see the fault current level just went higher when F21 was not tripped versus case 2 when the F21 was tripped. And you can see what happens to the voltage when it was a 4 kV system. So when the 3-phase fault happened at the distant bus where F21 is, the voltage depressed so much, and then it doesn't recover if F21 was not tripped. Whereas when we tripped F21 within a given time, we would recover back and the system stabilized. So going back, I did not show that here. Okay, but so they used goose command when the protection was would detect a 3-phase fault. It would send a goose-based command all the way to the feeder, because it was one system when it comes to comms. trip the F-21 to save the system. It's such a corner case. Might happen once in a lifetime, but it would still save the system from a blackout, especially considering you're in Alaska and winter. So what we achieved through this HIL testing, we were able to validate the power system. We did the validation of the generator controls through SEL 751, which was all the controls I mentioned. And we have validation of the POWERMAX algorithms. We did protection validation. I did not discuss about this, but all the feeders had some amount of protection relays in them, which we were able to put in, at least for the most important ones, like busbar protection and some generator protections. We were able to do some test protections. And we were able to find some corner cases and special logic for the system stability, like I mentioned about F-21. And also, we were able to pre-tune the generator, governor, and exciter and save us a lot of time on site, having to pre-commission them. And it also is a great learning tool when it comes to learning about new things, new controllers, which you have not worked with, but as long as you're able to set it up as a hardware in loop, it's a great tool and you can play with it as much as you like. And it was really beneficial having to use RTDS system. I think that brings me to the conclusion of my presentation. I hope you all enjoyed it. Thank you very much. I look forward to your questions. Thank you.
Thank you so much, Asad, for your presentation, and thanks to our listeners for your questions. Please keep them coming. I'm happy to introduce our final presenter of this series, Bruce Rigby from etalumiSe. Bruce Rigby has many years' experience in the use of real-time simulators for university teaching and research, as well as for applied testing and investigation for the power industry in the fields of electrical protection, power system stability, and control. He is currently the simulator specialist at etalumiSe Limited and was formerly the technical manager of the Real-Time Power System Study Center at the Durban University of Technology in South Africa. Please welcome Bruce Rigby with his presentation, Experiences with Using the RTDS Simulator as a Tool in University Undergraduate Teaching.
Hello, everyone. As Katie mentioned, the title of my presentation is Experiences with Using the RTDS Simulator as a Tool in University Undergraduate Teaching. Before I get started on the main body of the presentation, I need to give a bit of background about myself and where this work is coming from. So, although I'm currently a representative for RTDS Technologies, I was previously an academic and an RTDS Technologies customer in South Africa at a university here. I was responsible in those days as the technical manager for developing and running a facility called the Real-Time Power System Study Center. And this was a collaborative initiative between two universities, the Durban University of Technology, where the simulator was housed, and my own previous employer, the University of KwaZulu-Natal. And then thirdly, Eskom, which is South Africa's state-owned power utility and the main funder of the center itself and the purchase of the RTDS simulator equipment. Somewhat unusually, although applied research was one of the goals of Eskom in establishing this RTPSS center, it wasn't the main goal. The main goal in establishing the RTPSS center was to address a critical skills shortage that was identified at the time in the area of power systems and power engineering, and then to foster collaboration between industry engineers, particularly within Eskom, and academics at universities around the country in these fields. This goes back to around the turn of the century, early 2000s, where IT was becoming a very hot topic for students coming into university, and power systems and heavy current engineering was kind of seen as an old, unattractive field. So we wanted to kind of show that technology was very much a part of power systems and power engineering. So by chance, the people from Eskom who were delegated to serve on the steering committee of this RTPSS center were protection engineers. And at the time, I had very little background in protection. But through working with these guys, it led to a 10-year collaborative partnership in which the RTDS real-time simulators were used to train undergraduate students in protection principles via final year design and thesis project assignments. And I was able to do that by working with the industry engineers from Eskom on projects that they wanted me to carry out for them and help them with on the simulators. So I was doing and learning protection and doing applied studies and testing for the utility protection engineers using the simulator, and that filtered down into me being able to give realistic and challenging projects in the area of protection to the students I was teaching and responsible for at the university. It also spawned a whole new graduate research area. So as I say, my background wasn't in protection when I started out on this road. I was a power system stability guy, but it opened up a whole new graduate research area at our university. So in addition to protection systems, I was responsible for a final year undergraduate course in power system stability when the simulators first arrived in my life. So I also used the simulators in the area of undergraduate teaching in my original area, both in the form of final year design projects and as a platform for live demonstrations of stability phenomena during selected lecture periods. So I'm trying to share my experience with how I was able to use this as a teaching tool in both of those two areas. So the focus of the presentation is, since many real-time simulator installations at universities are research focused, and understandably so because it's very expensive and high-end equipment, my presentation is aiming to share some experiences from an alternative use case that can also be used very effectively in undergraduate teaching. In particular, how we dealt with the challenge of training final year undergraduate students to use a real-time simulator in the limited time that you have with them, and to connect hardware protection and control equipment to the simulator. So not just use a simulator, use it in anger for hardware and loop testing during their projects. In addition, we had the challenge of, for final year thesis projects, the ethos of the thing is really that the students are supposed to work independently and in an open-ended form. It's not supposed to be a hand-holding exercise. So how we managed the challenge of needing to do quite intensive training and make sure the students knew what they were doing on the simulator with the needs of a capstone final year thesis project course where you're supposed to leave the students alone to do open-ended self-directed study. So I'm going to discuss some typical real-time simulator project assignments and how we handle that kind of challenge between training the students and leaving them space to open-ended work for their projects. So the teaching and learning approach for final year RTDS simulator projects was, our semester was 13 weeks in duration. So out of that 13 weeks, kind of just divided the projects into 3 key stages. In the first 1 week, 5 days, we had intensive pure student training, which is not normally part of a final year thesis project, but we needed to do that so that the students knew how to use the simulator. We then kind of transitioned into a semi-structured intermediate stage of approximately 2 weeks, where there was still some close oversight of the students. They started to work independently on the simulators and their project hardware. And then finally, we take the training wheels off and let the students work more or less independently on self-directed work, where the academic is really providing traditional project supervision only, not close monitoring or checking of the students' work for about 10 of the 13 weeks. And the way that would work was we would start the highly structured initial 1 week simulator training would be very similar to what you get as a customer when you purchase a simulator, teaching the students firstly to compile and run simple power system cases in draft, and then execute them on the real-time simulator hardware in runtime. Okay. And then because the focus is on protection relays, we would teach them to configure input and output for hardware and loop tests, with the objective being ultimately to connect up a protective relay hardware. And this didn't matter whether the students were doing protection projects for their final year thesis project or power system stability and control projects using the simulator. We would train them as though they were going to do protective relay hardware, because the skills are more or less transferable. So teaching them I/O, we would start with analog output. So we teach them to configure sending analog output from a current transformer, and then show them in a hands-on manner how to wire up the output card through an analog amplifier and connect those inputs to the the outputs of the amplifier to the measurement inputs of the protective relay hardware that we use for training. We then show them how to configure digital outputs to send the status of a circuit breaker out from the simulation model, and then show them how to wire up the front panel of the simulator through the HV interface into the binary logic inputs of a training relay. And then lastly, we would teach the students how to configure digital input so they could read in the output of the trip or close contacts from the output of a protection relay, and then show them how to wire up the output contacts of the relay into the low voltage front panel inputs of the simulator itself. So they would have a complete closed loop implementation of a very simple overcurrent protection relay. And I've left that to last because it's an important part of the discussion and the philosophy of how we did the teaching. We deliberately focused on very simple examples and a very simple protection relay that was not going to be the relay that students would use in their actual project. So the focus of teaching them this was how to do stuff in RSCAD, not how to work the relay that they're ultimately going to use for their project. And for that reason, we deliberately focused on a very simple overcurrent relay that didn't require any software to program it. These were old relays that were stripped out of a substation and were donated to us by Eskom, the funder of the center, and literally had two overcurrent elements, phase and ground, and you set them with screwdrivers on the front panel. So you can literally teach a student how to set these relays in 30 minutes. And the focus here is not on the relay itself, it's on how to connect the relay for hardware in loop testing. One couldn't go and purchase a relay like that nowadays. They're kind of out of date. But you can get modern equivalents of the same kind of relay if you're interested in this kind of approach. So you can get very simple, lightweight relays from a number of manufacturers. This one in particular, it's also a very simple overcurrent relay. You can turn on you can activate one overcurrent element, and you can program it without needing fancy software. You can literally dial into it with an internet web browser and set the pickup level and the time dial level of the overcurrent element, and very, very simple relay that doesn't detract from the focus of the training. Then we would move to the semi-structured 2-week intermediate stage, and during this stage, the students would start to work on their own. They would first be told they had to implement their own model of the actual system that they're being given as an assignment to protect in their finally designed project. And the system would always look from a topology perspective more or less the same. Two sources at each end, two lines, one protected and one a parallel line, and they would have to interface to that two high-end multifunctional digital protection relays. Typically these would be impedance relays, but they didn't have to be. Okay, and everything in the two red boxes, the students would be responsible for by themselves. They would get no further assistance. They'd have to model their own system. They were given parameters and a settings objective, but they had to implement and model the system themselves in RSCAD, and they had to learn the relay without any assistance. So they were given the relay and the manuals. Typically these are fairly complex industry relays with several hundred-page manuals that the students had to master on their own. So fitting with the kind of ethos of a finally designed project. The only thing that the students were watched and assisted with, and not really assisted with, but supervised, is to make sure that they connected the amplifiers up correctly. So all the skills to connect the amplifiers and do the hardware and loop connections were taught in the initial 5-day training course. The students would do this themselves, but I would monitor and make sure that this is all correct. They would do a dry run, and we would see that the connections were done correctly, the fault logic is programmed correctly, so that everything was safe for both ends of the scheme. And then more or less I'm satisfied that the students know what they're doing and they can't do any harm to my simulator. Okay, and then they can be left for the remaining 10 weeks of the course on their own to solve the particular settings challenge that they're being given. On the next slide, I just want to focus on the fact that despite the fact that every student is given a system that looks very similar, you can make multiple unique settings projects for students year after year by following the same structured approach. So looking at that standard topology that we use for fourth-year projects, you can make it different in a multiple different ways. You can give each student different system parameters at a minimum. So for example, one student can be given a 275 kV network, another can be given a 132 kV network with different parameters. The students can each be given different relay communication schemes for impedance schemes, permissive overreaching, permissive underreaching. Each time you're making it a completely different project effectively, so the students can't go to school on other students' work. You can introduce high impedance faults. You can introduce rotating machines, again, making it a whole range of different unique projects for every single student. And the degree of difficulty of all of these different things you can match to the level of initiative that and ability that the student is showing. Okay, so just picking that last one as the particular example that I'm going to go further with. The student that we threw rotating machines at, the example of her project was we used Kunda's 4-generator 2-area system as the benchmark that they had to put a protection scheme in and prove not only that they could do protection between buses 7 and 8, but also that the protection could discriminate between electrical faults on the line and generator swings that looked like faults under transient conditions. So the student would not have implemented this themselves. They would have started with a system that looked like the conditions on the previous slide between bus 7 and bus 8. It's more or less the same topologies you saw before, and they would start with ideal sources at either end and develop that themselves. When they had implemented their hardware loop and got the protection scheme working between bus 7 and 8, I would then give them a working version of the full Kunda scheme, which matched their case between bus 7 and 8, and then they could say, all right, on top of your protection settings that were able to identify faults between bus 7 and 8, now show me that you can know the difference between a fault between bus 7 and 8 and a remote fault that might cause the generators to swing and look like an electrical fault between your protected buses. So an example of the student's result: for a fault on the protected line, the impedance looks like this and the relay would trip correctly. For a fault remotely near generator 3, you can have two different scenarios. The generator starts swinging and the seen impedance on the protected line comes in and out of the protected zones, which looks like the relay should respond, but because it's gone through the blinders in a continuous fashion, you can discriminate and see that that's not a fault that the relay should respond to. And then if you apply that fault at bus 11 for longer, you can cause the system to break apart, where you get the electromechanical swing coming through the zone and then going out the other end. And this is a stable swing and an unstable swing, which the settings can be programmed to respond to appropriately. So that's a fairly complex settings challenge for an undergraduate student, but is illustrative of the fact that with the right student and the right structured training approach, you can combine both structured training and completely open-ended, quite significant challenges for a student at undergraduate level. And not every student is able to go that far. You can set the additional challenge based on what you know about the student's ability. Skipping through power system stability and generator controls, some of the 4th-year project work that I gave out in this area, starting with single generator infinite bus systems using Prabha Kunda's classical textbook on power system stability and control. There's a single machine infinite bus example case there, where the focus is on the impact of generator excitation controls on generator stability. So the student would model the single machine infinite bus case from Kunda's book in the simulator, including a model of the excitation controls, the automatic voltage regulator and power system stabilizer. But the project itself was the student had to build and implement the same AVR and power system stabilizer in hardware on a Siemens programmable logic controller. So they had to discretize the equations for the existing excitation control scheme, implement them on industrial hardware, and then connect that Siemens PLC hardware in loop and prove that it responds in the same way as the simulated AVR and PSS. So you can hand over controls from the all simulation model of the excitation controls to the student's implementation of the same thing in hardware and prove that it responds accordingly. So the student's result, you can see here, we would throw a fault on one of the 2 feeders and the response would be to trip that line out. And then when the generator starts swinging in response to that fault and clearing the line, you can see the response of the output of the AVR, the field voltage, and the simulation model and the PLC implementation of the AVR controls are more or less sitting on top of each other. You can see the angle on the bottom plot, the angle between the internal generator voltage and the remote system. Once again, the all simulation implementation and the hardware implementation of the AVR and power system stabilizer are giving you the same response. So the student was implementing an already existing excitation control system design on hardware and testing it using the simulator instead of using real power system plant. Sticking with that area of work, generator controls, I gave a student a project where, once again, the same system, Kunda's single machine infinite bus case, with the AVR and a governor implemented. But here the student's objective was to develop an external controller that had to provide set point inputs for the excitation control and the governor control that's part of the real-time model, with the objective of providing inputs to the governor and the AVR to run the generator from standstill, and then tweak those inputs so that the conditions across the open breaker are correct, that you can synchronize the generator. So basically an automatic synchronization and automatic run-up and synchronization control of a single generator. And then lastly, to close out the presentation, I'll just focus for a few minutes on some of the all simulation demonstrations that I put together myself, either as class demos for my power system stability and control course, or as laboratory examples to let the students learn how to do protection settings, but in an all simulation environment. So starting with that one first, I developed an all simulation implementation of an example from the Alstom Network Protection and Automation Guide, which shows you how to do overcurrent grading. So this is an example of that example 921 from the Alstom Prag manual, as it's colloquially known. And there are about 9 different breakers at which there's overcurrent protection relays, and you're supposed to be able to show, okay, set these ones first and then grade these 2 relays against that, and then grade this one against these 2, and so on. Classical overcurrent grading. Now here I'm using the simulation model of an overcurrent relay from RSCAD's Protection and Automation Library, and then setting it up so that in runtime you can click on each one of these boxes and you get the settings inputs for each relay. So you've got the time multiplier and the pickup current, and you've got a dial that you can select whether it's a standard inverse or a very inverse, all of which are parameters of the relay. So these all are settable before you run the case, and once you run the case, they draft variable parameters that are kind of locked in for the duration of the simulation. So it meant that students can do overcurrent settings calculations and set the relays here, 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 and here, and then apply faults and verify their settings and their grading. Getting back to generator govern and excitation controls demonstration, this is more or less an all simulation implementation of the same 4th year project I described earlier, where the simulation models of a single generator with AVR and governor controls, and then you can manually start the generator running when it's at standstill, bring the generator up to speed by adjusting the input to the governor, bring the terminal voltage of the generator up by adjusting the reference input to the AVR, all while the breaker is open. And then you can start monitoring with a synchroscope that's built into the runtime interface and check lights to show you the conditions across the open breaker. So what is the relative speed and phasing of the voltage at this end of the breaker versus the voltage of the live system. And then when the synchroscope is at top dead center and all 3 check lights are lit up, so your voltage magnitude, your voltage phase, and your frequency are within tolerance across the open breaker, then you can manually press the close button and close the breaker. In the same case, once you close the breaker, then you can switch to a different panel in the runtime screen that you can open, which will basically show you a live phasor diagram plot of the synchronous generator and the PQ chart of the machine. So you can teach students as you adjust further, once the generator is synchronized, if you increase the input to the governor, you'll start to get a load angle between the generator and the rest of the system. You can see the phasor diagram respond live. And then if you increase the excitation, you can have an overexcited or an underexcited generator, and you can look at the active and reactive power on the PQ chart. And on the PQ chart, you've got the maximum field current limit and the 1 MVA circle described, and there's a little blob there to show you live as you change the settings, how the phasor diagram changes and where you are on the PQ chart and where you are relative to the generator's limits. It's a very good teaching tool to show students both how simulators behave before synchronization and after synchronization, both from a phasor diagram machine's perspective and a PQ chart power system operating perspective. Then I've got 2 classical stability examples from Prabhakunda's textbook, one on inter-area modes and power system stabilizers. So this is a 2-area 4-generator system. In area 1, you have 2 generators, and then you have a weak transmission system. In area 2, you have 2 generators. And this system is designed to show the impact on inter-area oscillations of the power system stabilizers at each generator. So with all 4 generator stabilizers turned on, the system is very stable and rock steady. Then as you turn the stabilizers off 1 generator at a time, it gradually has less and less damping of the inter-area mode until you turn off the stabilizer at the last generator you choose to disable, at which point the angle across the system starts oscillating in an unlikely negatively damped but unstable condition. And you can monitor the angle across the system, the speeds of the generator and the power transfer across the line, and you can see these unstable oscillations slowly growing. And the system has just enough negative stability that it can run for several minutes before it actually collapses. It gives you time to demonstrate the issue, and then you can turn one stabilizer back on again, and the system will come back if you intervene in time. We've also found this is a really good system to show people how to use the phasor measurement unit testing approach in the simulator, either with simulated PMUs or hardware PMUs. A very nice system to demonstrate PMUs using the real-time simulator. And then lastly, voltage stability and voltage collapse. Again, this is a classic example from Prabha Kunda's textbook to demonstrate long-term voltage instability and voltage collapse. So the system model looks like this. You initiate the problem by switching out one line, and then you have remote generators and a local generator. And by switching out this line, you get a drop in your downstream voltages. This is a 500 kV bus, and then into your distribution network. The tap changer at this transformer starts to respond to try and bring the voltage at this bus up, and in doing so, it draws more reactive power from the local generator. This generator then goes into field current limit, and ultimately the voltages of the system collapse. This all takes about 5 minutes. So that the x-axis of the simulation is about 300 seconds, and it's slow enough that you can describe what's going on and watch the different limits and the tap changes and explain to students what's going on as it happens. And by the end of the simulation, you've seen the same voltage collapse scenario that you see in the textbook, but it makes a huge difference to be able to show it and describe it interactively as it runs. Both for undergraduate student teaching, but this same case example I've used in many industrial training, continuing professional development training courses that I give to utility engineers. This is always a very interesting and popular demonstration, even to graduate engineers. So in conclusion, in this presentation, I've tried to share with you some experiences of using RTDS Technologies real-time simulator platform as an undergraduate teaching at a university, not just we did research with it, but we also used it more for undergraduate teaching than in research. So although many universities purchased simulators for research work, our experience was that these facilities can also be leveraged to enhance the education of undergraduate students as well. And in doing that, we found our research group and its profile was greatly enhanced, and we were able to leverage further industrial funding as a result. So we went from being a 1-rack simulator customer to being a 10-rack simulator customer over a period of several years, as a result of being able to deliver on the mandate that Eskom wanted, which was improving undergraduate teaching and attracting students into the area of power systems. So that concludes the pre-recorded part of my presentation. I'll be happy to take your questions once we switch to the live session. Thank you.
All right, thank you so much to our presenters today, Bruce and Asad. We so appreciate your presentations. And thanks to all our listeners for joining us for this final session of the User Spotlight series. Let's begin with a question for Asad from Schweitzer Engineering Laboratories. So Asad, you mentioned a couple times in your presentation that HIL testing was really valuable for you in demonstrating performance to the customer and in avoiding downtime on site. So I think it might be interesting if you could go into a little bit, if you didn't have an RTDS, how would that change the way you do your testing? What are your other methods for improving the operation of your systems?
Yes, I hope you can hear me.
Yes, it sounds good.
Okay. So we know our load shedding systems and our own algorithms. We've also done this in the past where we'd have to create static simulators for each system because we were directing our test for those particular just for this particular applications and algorithms, what we built in our controller. So we did have static simulators that we could test, but it would still not be real-time testing because we would have to pre-set up any case and using some kind of a simulator, and we would have to test each case, at least know beforehand on how the system is going to be expected. So our tests were limited to knowing exactly what the algorithm could do and just trying to find errors in our own control system. But we would never try to understand it before that, how it's affecting the power system in general. Like if an event happens, we're not sure if it's affecting the stability of the system or not. So HIL having to create a model of a power system we're testing really enhances our performance and trying to find any errors in our own control algorithms, or trying to find better solutions to validate and give a better solution.
Great, thank you. Let's go to a question for Bruce. So, Bruce, a lot of the time, offline simulation tools like PSCAD, for example, are used in the undergraduate environment rather than real-time simulators. I think partially for the reason of investment, but also because maybe the closed loop part isn't, really considered critical at the undergraduate stage. I wonder if you could go into how you think that hardware in the loop, closed loop aspect benefited students compared to examples like PSCAD or even having an open loop relay test set.
Yeah, thanks, Katie. Can you hear me?
Yes, sounds clear.
Yeah, okay. It's interesting that you mentioned PSCAD because I used to use it as a kind of a ramp up. So the simulator is quite a challenging environment for students, but we used to run all simulation projects in the first semester, final year, in PSCAD on protection as well. And it kind of brought home the level of detail that you could put both the hardware and software difference, as well as the real world nature of the protection relays. So the main benefit, in addition to physically wiring up relays, which you could do if you had secondary injection test sets, but the difference between simulation only tools versus hardware and loop primarily was just being able to set the students real world projects and have them work on actual commercial relay hardware. So I very much wanted those students to learn by themselves how to set a fairly advanced numerical protection relay, which would not be possible at all using an all simulation environment. We had a system where some of our external examiners were practicing utility engineers, and they would comment that the students we were graduating were kind of 6 months away from being able to do an industry settings project, whereas that would be like a year and a half before a normal graduate student would be able to take on a challenge like that. So it very much made a difference in the level of practical education the students were getting, but it also was hugely stimulating to the students that they could take on real world projects like this that wouldn't otherwise be possible.
Right, thank you. That's great. Let's go to a different question for Asad. Related to the modeling of the generator. So when you were doing your generator control testing, which model did you use in the RTDS simulator? I wonder what level of flexibility was required from you when you're modeling those generators. Were you simulating any internal faults? Did you take advantage of many of the features available? Or if you could give us some detail, that would be great.
Yes, Katie. In the group I worked with, we usually do not test that level of protection, of having to test any internal faults or more functionalities of the generator. We are more looking just for the sake of the power system stability. We have another group who would study them at the level of internal faults and any other protection functions that they have to test with. So my group in particular is still just trying to concentrate on control systems. So we did not have to go to that level. We were more than happy to just use the IEEE model of the generator, the simplified one.
Great, thank you. I apologize if my sound quality has decreased at all. We're having some construction at the RTDS Technologies headquarters, so it's a little loud over here, but we're excited to expand our facilities for sure. I have another question for Bruce. Bruce, you've kind of touched on this knowledge or expertise gap specific to protection engineering between graduating undergrad students and then moving into the utility space. Do you think that gap is particularly pronounced where you were teaching in South Africa, or do you think it's more of a global problem? Have you seen the type of teaching that you were doing used in other universities in other countries?
The answer to both questions is yes, I haven't seen similar gaps. And in my experience, though, is if you have a tool like this, you can very much overcome that gap. That was kind of the thinking behind the investment in that facility, was to try and both stimulate interest in heavy current engineering as a field, but also to bridge that gap, and it very much works. I've seen going to other universities around the world helping with RTDS installations. I've definitely seen, even at undergraduate level, it's not as common, but there are one or two universities around the world that are doing similar things and with similar results. So the kind of message is there, if you're in the fortunate position that you have this level of facility that you can use even at undergraduate level. I've seen it in other parts of the world too, where if you stimulate students and put the bar high, they're able to take on the challenge and do exciting things. I saw at the University of Qatar, the students were doing hard PMU projects on some of those Kunda examples at fourth year level. It's definitely a stimulant and an educational outcomes amplifier for sure.
Yeah, that's great to hear. I know, particularly for me in my undergrad experience, we had nothing like that related to protection, and I think it would have been very handy to have hands-on experience like that. So, okay, let's go to a question for Asad. The governor model that you brought in from ETAP, I'm assuming that's because the actual governor design was, of course, not available. So you brought that model in and validated it. Could you talk a little bit about how you brought that model into the RSCAD environment?
Yeah. Well, I didn't actually have to import or export anything like that. Usually, with most of our projects, we try to reach out to every manufacturer and try to ask them for more details that will help us better model their systems. So that we don't try to guess right from the scratch. The 2301E model was really fairly easy to build, and I just built it in our RSCAD model itself. And after that, we realized it wasn't exactly how it was. We did reach out to some people in Woodward, and we also found out that if you see the 2301E model, what's in ETAP, it just shows a PI control, but in reality, there's a PID. And we did have to test it extensively to make it more and more similar to how it was. So our intention was not only to match the response, but actually build the governor in such a way that whatever values you put in the hardware 2301E, we do the same values in our own model. So that kind of translation would be nice. We could not keep it with us, but at some point we want to build a lab that way and have that flexibility to play with it, and something similar to what Bruce was mentioning, and having to learn from these experiences.
That's great to hear. Thank you. I think we are just about out of time, so we will have to wrap this session up. I want to thank you again, Asad and Bruce, so much for your presentations. And a big thank you for our audience for sticking with us through this series. It's kind of sad it's the last session. But as I mentioned, we will have a survey that pops up on the exit. And if you would do us the favor of giving us some feedback, that would be very appreciated. And with that, I hope everyone has a great day and stays safe and well.